So today I'm going to speak on pharmaceuticals or Pharma 4.0, advanced manufacturing of biopharmaceutical products. And my primary appointment is in chemical engineering at MIT, but I also have affiliate appointments in several centers, including the Center for Biomedical Innovation. So I'm going to talk about Industry 4.0, and this goes by various names such as Smart Factory or Factory of the Future. And for this symposium, probably all of you know this definition. The current trend of automation data exchange that includes cyber-physical systems, IoT or IIoT, cloud computing, cognitive computing. This is an image to give you sort of a feeling for that. So here's the I 4.0 Smart Factory. And this is a nice image I got from Dirk Decker that sort of outlines and describes sort of all of these components. What I'll be focusing on is on the data and the controls. And so that's really going to be associated with the bottom parts on smart production traceability, as well as condition monitoring, predictive maintenance. And generally, Pharma 4.0 is the term that the pharmaceutical people are using for adapting Industry 4.0 ideas to pharma. And Biopharma 4.0, of course, is the similar sort of adaptation to biologically manufactured drugs. Now, I'll be talking very much about digital manufacturing, advanced manufacturing, but I won't be using that terminology directly, but I would say I'm going to define it just so that people will sort of understand where I'm coming from. And so here shows a automotive facility in which, most people imagine this as digital and advanced manufacturing. So I'm actually going to be talking about those things, but I'll talk about it within the context of chemical processes. And it'll be in terms, and biological processes, I'll be talking about it really in terms of these very precise definitions. So digital manufacturing is an integrated approach to manufacturing set around a computer system. So everything I'll be talking about will be set around a computer system. And advanced manufacturing is this is the definition that the Obama White House and a committee that Obama created some years ago on advanced manufacturing. This was the definition they used. And so that's the definition that I'm going to use as well, which is the rapid transfer of science and technology into manufacturing processes and products. So it's very precisely that definition. And the focus of my talk is all going to be about that. So how do you, as rapidly as possible, if someone develops, let's say, a new drug, how do you get that drug to the people where it can do therapeutic benefits as fast as possible? And it's going to involve a lot of data and controls. So that's really the steps and strategies I'll talk about for getting that new invention, in this case, a drug, out to the people. Now, this idea of Pharma 4.0 is not really new. It turns out that there was a case study that collaborators and I did back at MIT some years ago, about a decade ago, where we actually, manufactured, designed a plant fully digitally, and it's all centered around a computer. We built all the controls all by computer. We built the simulations by computer before we built the plant. And then we built the plant. It was actually built at MIT. And we actually reduced costs by about 50% of both capital and operating costs. And we met all the purity specs the first time we closed all the control loops. So we closed them all just like we had predicted in the simulation, and it worked first time. And so this has actually been done before. And so it's actually done quite some time ago. That was for small molecule pharmaceuticals. This would be like tablets. This is all chemical stuff, so it's all chemical engineering. So it's all a bunch of chemistry and separations. Those shows the product crystals that we had that was made by our manufacturing plant. And it was almost manufacturing scale. And we all did it all in about a 2-year period, which was also a record in terms of speed. So I'm going to be talking about a continued adaptation of the procedures that was used for that process. And so we've been continuing to develop the different technologies over that time to make things more efficient and faster. And we've also been applying it to lots of more systems, mostly actually in biologically manufactured processes as opposed to chemically manufactured. And so over the years, we basically have defined and honed and tuned 5 strategies. And it's all been about how do you, as quickly as possible, come up with if you get a new drug that's been invented, how do you get that into manufacturing processes and into production as fast as possible. So this is in industries called process development. And so it's basically, how do you automate process development, make it fast, make it efficient? And so basically, how do you replace a whole bunch of bad decisions and slowness and inefficiencies with basically, algorithms, so computers and robots, which in this case are typically, pumps and flows, and sensors. And so that's really what this talk is going to be about. So, and the way I'm going to structure it is I'm going to define the 5 strategies, and then I'm just going to have a lot of examples. And I'm just going to take example after example of the application of these strategies, so you can see that these aren't abstract things. These are very precise, very concrete things. And you can see many examples of how we apply those strategies to many different examples. And I picked examples from about half of the examples that we've done in our own group. So there's another half, and I'll give references later for people that are interested in other examples. So the strategy are really, number 1, is greatly increasing understanding and optimization of each unit operation, exploiting process intensification. And this is typically related to continuous manufacturing, but it doesn't necessarily have to be. Sometimes you can come up with very efficient batch processes. But it's really taking it to a level where you have so much understanding that you can really accelerate things, because you're not so much sort of looking in the dark. I'll also give examples of automated micro-scale technology for low-cost data collection. And so the idea is you design these systems that are micro-scale systems that are fully automated systems that you can run at very low cost to collect a lot of data. And so I'll give various examples of that kind of technology. I'll give examples of plug-and-play modules with integrated control and monitoring to facilitate development. And so the idea is when you put together a plant, you synthesize a plant, you should have a physical plug-and-play unit, things like bioreactors, chromatography columns, crystallization systems, and you should be able to have the digital version of that, the digital twin, at the same time. And when you plug and play in the software, it should be the same as the physical. So if I plug the physical systems, they should auto-recognize and the software is connected. If I do the software should be able to send the message to a robot that physically connects things. So those things become then seamless between the physical and the digital. I'll talk about the role of mechanistic modeling for the unit operations and for plant-wide simulation and control design. And then I'll talk about data analytics. And these are basically strategies that you use when you can't do things mechanistically. So how do you do that, but do that very efficiently? So it doesn't require people. You're going to have it done by largely by robots, and you have experts that come in that understand what's going and plug and play, but they're focused on tasks rather than dredging through a whole bunch of reinventing the wheel and doing things very inefficiently. Let's do it very efficient. So instead of taking 8 years, for example, it was the normal for a vaccine. Can you do it in 1 year? They actually did it for COVID-19, but you now do it low cost and cheap and do it over and over, so that you can provide vaccine very rapidly and efficiently without having it to be a life and death for the world kind of situation or pandemic situation. So, and how do you do that for lots of other different health type products? Now, I'm going to give my examples all from pharma and biopharma, but the same strategies actually work for chemicals, so they work for small molecule pharmaceuticals are just chemicals. So it's for chemical engineering. It would also, many strategies also work for mechanicals and materials and related types of things. But to keep it sort of more narrow in scope, I'm going to be focused on healthcare type applications. So the first example I'm going to do is an example in which it uses continuous manufacturing and process intensification, and it combines that with mechanistic modeling. And this is an example actually for vaccines. And so historically, vaccines take a long time to develop. Flu is produced every year. So they take 4 strains, and it takes them about 5 months from when they identify the strains to when they start poking people with needles. The problem with that is they guess wrong half the time. So half the time they pick the wrong 4 strains and everyone gets sick, okay? And half the time they pick the right 4 strains and then nobody gets sick, okay? So the question is if you could shorten that time from 5 months to 1 month, now you could pick the right 4 strains almost every time. And then you don't have these weird seesaws where people get sick and no one gets sick and everybody gets sick. So you actually have like no one gets sick, or almost no one gets sick. So at least if they've gotten the flu shot. So how do you try to do that? Well, you have to move towards a different way of doing things. And so what we have here is where instead of making a vaccine in eggs, we make it in bioreactors, as shown here. And the idea is that you then currently people have developed the technology, but they do it all in batch. So they take a batch bioreactor, they grow it up, they put it in another bioreactor, they grow it up, put another bioreactor, they do it a bunch of times, and then they infect all the cells and they harvest. And the infection and harvest takes about a day, and all the process to get up there takes about a week. So about 6 days, they're not producing anything. And only for a day, they actually infect and produce virus. This is for viral vaccine and actually do the harvest. So if you move it to continuous, you can get a factor of 5 right away by just having a host cell reactor that creates host cells continuously. And you just keep throwing it over the fence to bioreactors, and those infect the cells and do the harvest. You just do it continuously. So you're always producing. And that can give you a factor of 5. So what's showing you here is we worked, there's mechanistic models that have been developed and experimentally validated. And what we have here, if you choose one viral bioreactor where you're infecting the cells, you get these large oscillations. So they're actually by about 5 orders of magnitude in some of the states. That's bad. You don't have uniform product quality. You can show that it actually reduces your overall yield. Now, it's been shown proposed in Europe that instead of using one continuous bioreactor, if you do 5 of them, you can make these self-induced oscillations go away. And you can see if you choose 5, you get this black line. You basically get no oscillations. These oscillations have been studied in great detail, and they're all captured by the model. So we can actually simulate all this and test it out quite thoroughly. But it's kind of bad, right? We moved to continuous, but now we've got 5 bioreactors. Well, that's not good. That's not very condensed. So we decided, let's try a different strategy. And so for that strategy, we have one bioreactor, but we introduced another type of strategy known as process control. So just by putting a feedback controller on a single bioreactor, you can get rid of the oscillations. You can increase the overall yield. So you only need 2 small bioreactors instead of 1 big one. And you can produce all the time and get your factor of 5. We're actually working with a couple of companies now to test this out experimentally to see if, yes, can we actually do this and get that factor of 5 improvement in vaccine production. Here's another example in which we use mechanistic modeling and combine that with process intensification. This is for dealing with genetic stability. So when you look at these recombinant type organisms, these recombinant organisms, they make protein, you genetically engineer them, but it turns out their genes are not stable. They'll tend to get rid of them. This one is actually for an application. It's actually another vaccine. It's for recombinant vaccine, what's called a subunit protein vaccine, where you basically just create the cells, you modify the cells so that they create proteins that are on the surface of the vaccine. And that's actually the way the Pfizer and Moderna ones work, but they manufacture inside your cells instead of manufacturing in a separate system. But what happens is you go ahead and put what are called copy numbers to be able to produce these surfaces of the viral codes, the surface of they're called capsids, the outer part of the viruses. But what happens is there's biology that'll tend to take them out. And that's what's shown by these red things. It just biology goes in and just tends to take these things that aren't what the cell's supposed to be producing, and so they just pull them out of the cell. So the question is how do you handle that? So we just wrote down a detailed model from the biology. It actually has a single parameter node alpha that has biological meaning. It's actually the rate at which copy numbers, which are your copies of the proteins that are being pulled out. We did this, just read some papers, wrote this out. It actually fits all data that's been peer reviewed for all Pichia pastores. So it describes all of that process. And you say, okay, well, that's great. You can describe that. What do you learn from it? Well, we then use that to propose another continuous process in which we could increase productivity by getting rid of this issue about pulling out copy numbers. And so the way we do that is we basically set up, again, a multi-bioreactor system where we've got a production bioreactor shown here. And then we have a perfusion seed reactor where we just have this extra reactor that's designed so that it doesn't have this copy numbers taken out by having a different feed. We actually feed it with glycerol. And then what that'll do is that you can always maintain the small reactor that always has full copy numbers. So it's always fully productive. And then we can just bleed that using our model in the right amount into the perfusion, so we can guarantee that that fusion bioreactor always has high copy numbers and is always high productivity. So that gave a couple of examples with bioreactors. So now what I'll do is I'll do another example. This one is actually associated with a separation type process. So this is a system that we completely designed. Actually, the patent, this is a little bit out of date. The patent just got approved. And so what we have here is that it's, again, Pichia pastoris. So it's a high density type system. We said, okay, how do we try to deal with that high density, get high productivity? And so you need to get detailed understanding. And so we built a detailed model in Fluent. And what we found was that all the existing technology got clogged very fast. This is very dense stuff. It's almost like porridge, and it just clogs the system. And so what people would do is you try to use a traditional system, it clogs in about 2 minutes, where you're trying to take out the protein in the liquid that's in the bioreactor, but you can't take it out because it's all getting clogged. And so we went ahead and just designed a system where we took a whole bunch of hollow fibers, and instead of putting it external, we put it internal, so we could use all the internal velocity force field to give us enough stress that we could make sure that we don't foul these particular systems. We completely designed it in the computer. And so you can see some of the examples of the pictures. We used that to design the diameter of the hollow fibers and the spacing and the location within the bioreactor. And it actually worked first time. So first time, put it through, ta-da, stopped all the fouling. So this thing will last for hours. You can see here, we ran the system for 180 hours, in which we were operating in high solid density, and we continually take the material out. And now we have a plug and play unit. You just put it into the system, auto recognizes the software, and auto behaves and gives you a very nice removal of material without clogging. Again, entirely using a mechanistic modeling and process intensification. Here's another example. This was an in situ pH adjustment. It's another process that shows up, and not just for bio, but in other applications. pH adjustment is a very highly nonlinear process, but we needed to have a way of doing that very fast and very efficient with a small amount of dead volume. And it turned out that system didn't exist. So we said, well, let's invent it. So we went ahead and designed a system with very localized intense mixing. That's fine. People have proposed such a thing before. But what's been known in the literature is that you get very poor performance if you try to do this. So you can develop the best nonlinear controls. This is actually differential geometry controls. And if you do that, you can build it and everything, but a little bit of uncertainty will lead you to get poor controls under different pH set points. And so this is showing a detailed nonlinear, process control system. And under some conditions, you get big overshoots. Under some conditions, it's sort of okay. Some conditions, it's really slow. And this has been well established in the literature. And so people have solved it by using big systems. You basically use multiple big tanks, okay? But we couldn't do that. We need to actually use a very small volume for the systems that we were developing. And so what we did is we just said, okay, well, let's do that. So the way we did it is we actually used an adaptive controls that's just updating the uncertainty in the titration curve. And by doing that, we're able to get very, very high performance that you can see here for any set point. And so now we can put that thing anywhere in a process. We can put that in front of a chromatography column, put it after a chromatography column, put it elsewhere. Thing works, thing's robust, very, very fast, very, very small dead volume. Again, very intense, and again, using continuous manufacturing, using mechanistic modeling, and again, feedback controls, in this case, nonlinear adaptive feedback controls. Now, I've given you some examples of mechanistic model and process intensification and feedback controls of a couple of different types. So now I want to talk a little bit more about plug and play. And so this is a system that we actually developed. We've submitted this for a patent, and it's under review. This was another case in which we wanted to do viral inactivation. And so it's a step where you need to lower the pH for a certain period of time, hold it very, very precisely, and then raise the pH. And you don't want to hold the pH longer than you need to because you start to damage your compound, some more than others. And then if we don't hold it long enough, then we don't hold the pH low enough that it can destroy these certain type of viruses called envelope viruses. So what we did is we did full detailed mechanistic modeling. We built a continuous process. It involves basically a tubular process with some beads inside it. We use the pH control that I just showed earlier to control the pH upstream to acidify. That's what's shown here in the orange box. Then we do the low pH route, which is a tubular-based system, and we did detailed mechanistic modeling of that system so we could understand the residence time distribution. And then we do a basified step afterward to give you the pH that's going to go to a downstream chromatography system. This shows the set point tracking. What I'm showing here is actually all experimental results. They're almost indistinguishable from the model because we built a detailed mechanistic model for the system. We can show here where we're controlling the pH at different set points. We're controlling both at acidic conditions in blue and in base conditions in red. And you can see we get very good tracking using the system I showed earlier. We also built into the system negative tracer. So we actually inject pure water in the inlet, and that allows us to actually track in real time. And we can track each one of those inputs into the output and find a direct measurement of the residence time distribution and compare that with our mechanistic model. You can see that's showed here in this black and blue, where we do an injection and then we measure the output coming output just by a reduction in the concentration because we injected a tiny bit of pure water in the system. Fantastic set point tracking. We also have it for residence time tracking. You can see there at the bottom. Very, very exquisite control. Again, by using mechanistic modeling and using feedback control. And it's a plug and play system. So we designed it so we can plug that play into any of our processes. We've actually plugged it into another system that's in another person's lab with no extra software integration, nothing else. We just plugged it into the system and it operates. Here's another example we did. This is actually for a crystallizer system that we've used for both small molecule and large molecule. It's another plug and play automated system. It's a system we developed for over a series of years where we exploit a flow instability, which is another idea of process intensification. We also use micro mixers as well as ultrasonication that allows us to have controlled nucleation. Then we take a controlled nucleation upstream, and then from that, and this flow instability, we can get very good mixing just from internal flow that you can see with these whites shown here. We characterize that again in detail using mechanistic modeling as well as tracer experiments. And this multi-phase flow gives us very good mixing, even though we keep things in laminar flow. And that laminar flow allows us to get extremely high driving forces, about a factor of 1,000 higher than what you would do in a normal crystallizer, which means you would get a very, very small crystallizer that's about the size of a bucket, a little bit smaller than that. That's production scale. So very small. Instead of a big giant one, we have a very, very small one. This shows actually the controls. We did it all digitally again, that's shown here. We built a series of counter current heat exchangers that allow us to get spatial control. And that allows us to control the growth rate downstream from the system. It allows us to modulate impurity incorporation. We showed with the computer, just by doing simulations with the detailed controls, that you couldn't control it using the external flow rate, which is normally how you would do this. That you could control it, though, if you controlled the ratio of hot and cold flow with a fixed flow rate to a bunch of counter current heat exchange. Again, all done digitally. Then we built it, and it worked first time. So first time, model predictive controls, all the startup is all done automated first time. Now, you can't do this for an FCCU or fluid catalytic cracking unit for oil, but you can do this for a lot of these systems that can make very intense and where you're not having huge production rates because you can have very well controlled and get a lot of mechanistic information that you can use. And so that's why we've been able to demonstrate this time and again for both biological systems and for chemical systems. So now I'm going to show an example of all four of these strategies. So now we're also going to have automated microscale technology. This is actually from a colleague's lab. We've also published on this. So we built the state estimation and model predictive control system showed down at the bottom if you want really fine control. But they already had pretty decent controls already. It's not quite as good, but pretty good. And this is actually in an Irby biosystem, so you can buy it. Rajiv Ram is in electrical engineering. He co-developed this with Tony Shinsky in the Department of Biology. And what this is these are modules you can see here on the left. They're, again, plug and play modules, and you can stack them. There's actually, you can see 4 of them stacked here. And then you have in them all of the feed and all of the product are there. You can actually connect them all together into common product and common feed lines. And then what you have is you have on top of them shown here, this is a part that just snaps in. That's a little smaller than a deck of cards. And you can see a schematic of it up here. You can see the up there on the right, and where they use some colors so you actually see the images. And each of these different lines, these are actually flows in a bioreactor. And this is, again, a continuous bioreactor. They can operate this density so high that it's like toothpaste. And if you take like Pichia pastoris, it'll survive under those conditions. And you can actually get oxygen through a membrane. It's completely automated. You can see all the holes on the top for all the things, but it also has all of the optical density and pH and dissolved all the probes you would normally have in a bioreactor. All the sensors are integrated into the system. You can plug and play, directly connects to the computer, all has feedback control, all allows you to operate large numbers of systems in parallel, so you can do things like media optimization extremely quickly. This is another system that we've developed. So we've developed a lot of systems in our lab. This is the biggest one that we've done for bio so far. This is actually an entire monoclonal antibody line. So it's continuous. Monoclonal antibodies is one of the big biosystems that you have for, especially for cancer type things or oncology. And so a lot of the advances in cancer the last 15 years really monoclonal antibodies. And so we built in a continuous system. You can see here all the different units. And so we've been following all these strategies and applying these principles as much as as much as humanly possible. So, or technologically possible. It's very heavily instrumented so that we can get very early modeling, deeper analysis, and really build mechanistic models instead of just doing things using data-driven approaches. And we get the insights quickly and use that. Um, this shows the upstream. So we have 4 bioreactors. You can see a picture on the left, and it's very heavily instrumented. So it's about $2 million of sensing to give you an idea of the cost. So, but it's worth it, right? Because you can run a whole bunch of systems quickly and get that to the people much more quickly by this kind of technology. We're showing here that we have metabolites. So over in the lower left, we have all the normal bioreactor things you would have, OD, DOT, and pH, temperature and pH, but we also have a viable sensate, which you normally have. We also have it instrumented with a Raman and blue variant to give us off gas. So it's a very heavily instrumented system, but it's much more than this. What we also have is we have a mass auto sampler with 4 bioreactors with different ports that we can measure in real time things like chemical modifications to the protein. They're called post-translation modification profiles. This is actually a liquid chromatography mass spec system that we have set up that allows us to measure glycosylation profiles, which affect the performance of the product. And we can do that in near real time on the real process and incorporate that into model predictive control algorithms. Again, you get a new monoclonal antibody, can we put that through the system and start producing products as fast as possible? So then I've given you a lot of examples of some of the systems that we've looked at in our group. What I want to do is I want to actually talk about what's left. So it turns out you can't always write mechanistic models. We've done this for a lot of biosystems, including gene therapy and other systems I don't have time to present, where we've been able to just take the system, handle it like a control engineer, write down the network, write down the different steps, and build models and have them be highly predictive. And so a lot of times people say you can't do that. We've already demonstrated that many times, okay? And before me, there were people like Greg Stephanopoulos and others that demonstrated it long before as well. So often you can do that because you still satisfy material balances, energy balances, species balances. Energy balances, these things still have to hold. But it turns out there's always some things with biology and even in chemistry that you can't do that. And so for that, we've been using a machine learning type algorithms. So I want to give a little bit of an overview of the state of process analytics. So right now, there's a lot of time and expertise required to really select the best tool for a particular application. So a lot of people, and so why is that? It's because they come from everywhere. You have analytical chemistry like PLS and PCA. You got computer science methods like deep learning. You have applied statistics. It's all over the place. And so you need like 5 PhDs to really learn all those methods. And so in practice, people either apply the tools they know, which can produce suboptimal results, or they just apply a lot of tools and cross-validate to find the best, which has been well established to always overfit 100% of the time, okay? And so those are sort of the trade-offs, always overfit or apply suboptimal tools. And so what we've done is we've been working on very precise analysis to figure out an automated approach for this procedure. But the question is how do you do that? And so you want to make them focus on the goals and methods. You want to be able to fully automated by computer as you can, but how do you do that in a way that's really effective without just trying a ton of methods and hoping for the best? And so the way we've been doing that is by very systematically just interrogating the data and using metadata that's already available, like is this spectral data or not. And so we quantify the properties of the data. And then once we have the properties, we can select the best tools. And so far, we've been able to reduce it down for every type of data set to 2 or 3 tools. And if you cross-validate on 2 or 3, you can show that that's fine. When you run into problems when you start to do, let's say, 5 to 10 or more. So now it's basically a decision tree, or they would call in the 70s or 80s an expert system. But you can represent most of it in a simple triangle shown here. So you have collinearity, nonlinearity, and dynamics. And then we've done a lot of detailed analysis of all the dynamic methods. And we basically converge to these 3 methods. So CVA, MOSPIN, and SSARX. And so done detailed case studies as well as theoretical studies to support this. We then did collinearity. We did, again, detailed studies. Now we're focused very specifically on process data. So we're not talking about every possible data set, but we've done a huge number. Sometimes PCR is a little bit better, but it's rarely better than either ridge regression or PLS. So those are the methods if you're going to do a black box or dense type model. If you want interpretable models where you want a small number of inputs, so you're going to interpret for the output, then there's we found the best sparse PLS algorithm and elastic net algorithm. And we didn't include things like lasso because lasso is inherently known to be very flawed and to be arbitrarily sensitive to data. So again, we have all of it detailed in our publication. For nonlinearity, we have kernel SVR, support vector regression, random forest regression. And we developed a method called ALVIN, which was basically an algebraic learning method for interpretable models. If you're on the edge where you have dynamics and collinearity, you take stuff on the edge, would have it be the same as that. If you have nonlinear dynamics, then dynamic algebra or recursive neural nets. If you have nonlinearity and collinearity, then there's this. Now, I'm hoping this won't be the final version. I hope that people will find stuff that's flaws and come up with better algorithms and be able to keep replacing these. But they should at least run this free software that's available on GitHub and do a comparison when you propose an algorithm to see if it's better than what's the best that's out there. And all this is all open for source software in Python and R. So the only one we developed was Alvin. And basically what we did is we just defined a bunch of features that were based on what you see in chemistry, biology, and physics. And so we could represent that in terms of 4 basic mathematical operations. And then we just construct features from that. And that's a standard feature generate. And then we do sub-selection of features or feature selection. Very standard approach in machine learning. And so we use a sparse regression elastic net on those features. The dynamic version we call dynamic Alvin. Again, it's available for free. Now we've applied this on a huge number of case studies. I think the paper has like 80. This is actually the earlier case study. I'm doing this, like, this is on real industrial batch data from Biogen for 2 different manufacturing lines. So we had data input output for these red boxes shown here for bioreactors and chromatography. We originally developed it was motivated by this because they were getting some very strange results when they were applying PLS or response service methodology. They weren't quite sure what was wrong, but they thought something was fishy. So then we had to develop this to figure out what was going on. And this shows some sample results shown here. Yellow was the machine learning algorithm. And you can see they did quite a bit better than the other algorithms, which were the standard PLS and PCR, and had to deal with very particular quirks of this data set that wasn't captured by PLS because they were 2 different manufacturing sites, okay? And PLS couldn't handle that, or the machine learning could handle that. So, and again, it could handle it automatically. So I just have 2 more slides. So how to best use modeling and analytics. So always use the right model for the task at hand, okay? So first principles where possible, especially always, okay? If you can do that, because it'll save you a huge amount of time. High complexity when you're intensifying a process design, like the examples I had for developing something that would hold the cells in the bioreactor and just take product out of the bioreactor. Lower complexity for process control and quality monitoring. That's an example of the model we use for our pH. So we have detailed CFD models, but at this point, we just have 7 tanks in series that capture all the residence time distribution for our pH mixer models. Combinations of mechanistic and data analytics are supported by commercial software. This has been true for a long time. And so it's not so much well known outside of chemical engineering, but chemical engineers for at least 40 years have been running, PSE and AspenTech and Res Group like software. So they've been having software that allows you to simulate all kinds of mechanistic models and non-mechanistic models, including switching and startup and shutdown and changeover. And so, and sensitivity analysis has been built in for decades, either local sensitivity analysis using sensitivity equations as well as Monte Carlo. So you quantify all the uncertainties and all of that quite in a straightforward way. You can take more advanced tools. It's easy to wrap in. And so you just wrap in more advanced tools easily. You can also wrap in more advanced tools for dealing with PDEs. And it's just easy to wrap into any of this software. So the power of the software is there. That's not the bottleneck in the system. So I hope I've given you a feeling of basically Pharma 4.0. So, and again, I used examples all from Pharma, so I had sort of a coherent story. But the techniques I'm talking about are more general than that. Just more general for chemicals, materials, things where you're gonna deal, things where intensification is a useful strategy. And I listed these 5 strategies, and I gave lots of examples of these different strategies and their application. Is this really crazy stuff? It's not crazy stuff. I mean, most of those strategies were already applied 10 years ago when we built a plant at MIT with 5 of my collaborators. So mechanistic models were built, models were validated in the plant, put in a plant-wide simulation. It was used to design the plant-wide control system and the unit operations controls. That was all done in the computer before the system was built. The product was on spec once the control systems were tuned on. Okay, so didn't have to do a bunch of retuning or anything. It just worked. We took into account the uncertainties and disturbances. We included that into the control design. We've actually applied the same strategy now to a continuous process at Amgen, and this was just published in late 2020. All the same strategies all applied at Amgen. The technologies are all available. There's multiple startup companies. Continuous and Snapdragon are 2. There's also on-demand pharmaceuticals, and another company I can't think of. There's at least 4 spin-off companies applying these technologies now that spun out of this work. And I don't mean my work. I mean the work from all of the process intensification and strategies. And so that's from Tim Jameson's group in chemistry, Klaus Jensen's group in chemical engineering, and Alan Myerson's group, and Travis' group, and various people in chemical engineering. Now, our main activity in our group has actually moved away from small molecules, but still doing some work here. But we've mostly moved now to bio. So it's been these different kinds of therapeutics, vaccines, and gene therapy type products. So here's some references. So we have stuff that gives the perspectives and small molecule kind of stuff. That's the Amgen application. These are a series of papers on stuff that I talked about here, as well as some perspective work. This is some more perspectives. This is the stuff we had on smart data analytics that I talked about. This is a review on tensorial data analytics that I think is very promising for chemicals and for pharmaceuticals. I finished there with, which creates a huge amount of data. A single data point could be 1 gigabyte. Okay, so it's a lot of data fast. So how do you implement that data and use that data? That's for what's called hyperspectral type imaging and video. I have a couple of things there, just some other recent papers where we're doing things on vaccines. This is just a slide that just has a whole bunch of stuff on continuous manufacturing references, talking about the kinds of strategies that I talked about here in terms of controls and process intensification and continuous manufacturing and use of data in various ways. For acknowledgements, the material described work funded by DARPA, the Army, and the Navy, and the FDA and numerous companies. And I'm legally obligated, and it's factually true, that any opinions, findings, and conclusions or recommendations are my opinion. It does not necessarily reflect the views of the financial sponsors. So thank you for your time, and I hope there's some time for questions. Cheers.